So in this class, we'll briefly go over the design of IIR filters as we talked about last time. Since causal stable IIR filters cannot be made to have linear phase, we typically don't spend that much time. Most of us prefer to work with FIR filters, but I just want to make sure that you are aware of some of the basic concepts. So while FIR filter design in discrete domain or digital domain is very much a digital domain phenomenon. You get the impulse response, then you have this windowing operation and so forth. The IIR filter design is actually learned through the IIR filters that were designed in the analog domain. So IIR filter design is actually based on the design of IIR filters in analog domain. And again, just like the discrete IIR filters that can be implemented are the ones whose Z transform can be represented as a rational function of two polynomials in Z. You may remember that the analog IIR filters that can be implemented correspond to the ones whose Laplace transform can be written as a rational function of two polynomials in the S domain. So these are implementable IIR filters in analog domain. Okay. And we are not going to spend time on that. The reason we are interested in that is because before the digital systems arose, so analog design has existed for many, many decades, and it has been perfected over the years, and there is no reason that people felt to reinvent the wheel. What they said was basically, we'll take these designs that are already existed in the analog domain. In particular, we know very well analog Butterworth filters, Chebyshev. There are two types, 1 and 2, elliptic filters, elliptical filters, and so forth. And people have really perfected the design of these filters in the analog domain. So the decision that was made is, let's just take those analog filters and do a mapping. So take these filters, and by taking these filters, it means just take their transfer function h of s and transform them in a sensible manner to the Z domain. Okay. Because at the end of the day, what we know is that whether you are in analog domain or discrete domain, the frequency response is determined by the locations of poles and zeros. So if you have a way of mapping the poles and zeros of your filter from S domain to the Z domain, you get an equivalent filter with some sort of deviations. So just to remind you that in the analog domain, if you talk about S plane, so if this is the S plane, the frequency response, so in the discrete world, the frequency response lives on the unit circle of the Z domain. In the analog domain, the frequency response lies on the imaginary axis of the S plane. Right? Hopefully you guys all remember that. And similarly, just like the case that for stable filters, we want in the discrete domain, the poles to be inside the unit circle. In the analog domain, we want poles must be in the left half plane to be stable. And the other principles of what poles and zeros mean in the Z domain is exactly in the S domain is exactly the same as in the Z domain. In the S domain, if you have a zero very close to some location on the imaginary axis, that means that your frequency is getting pulled near that frequency. If you have a pole near the imaginary axis, that means that frequency is getting pulled up or amplified because of the presence of the pole. Right? So the principles remain the same, and what people said was, let's come up with a mapping. There are other approaches, but we are only going to focus on this. Let's come up with a mapping. So the basic idea is a map or a function or transformation from S plane to Z plane such that two conditions hold. So the first is you want the frequencies in the analog domain to be mapped to the frequencies in the discrete domain. And that's why you will somehow preserve the shape of your filter. If the idea is that low frequencies in the analog domain are kept and high frequencies get killed off, so you have a low pass filter in analog domain, you somehow need to map somewhat similarly. You can't map linearly, because in the analog domain your frequencies go from minus infinity to infinity, whereas in the discrete domain your frequencies go from minus pi to pi. But if you can somehow try to do this mapping in an intelligent fashion, you can preserve some shape of the analog filter in the discrete domain. So the first idea is that your map should do the following: imaginary axis in S plane should map, because imaginary axis is it corresponds to the frequencies, analog frequencies. It should map to the unit circle in Z plane, because that's what corresponds to the frequencies in the discrete world. And the second idea is that the left half S plane should map inside the unit circle, so that if you started with a stable analog filter, you will end up with a stable discrete filter. And based upon that, one of the most popular transformations, that's called bilinear transformation, is what is used. That serves this purpose. So the bilinear transformation basically says that the mapping is given by Z equal to 1 plus S over 2 over 1 minus S over 2. In the book, there is sometimes a factor T involved. That's a dummy factor that can taken to be any number, and so I'll just take T to be 1. So this is transformation in going from S to Z plane. Now, what does this transformation mean basically? You should really think of it in terms of mapping the poles and zeros. So what this means is, say, analog filter had a 0 at some location S naught. Okay, so if you had a 0 at a location S naught, the discrete filter will have a corresponding 0 at Z naught, which is given by this transformation 1 plus S naught over 2 over 1 minus S naught over 2. Okay, so a 0 will map to a 0. In general, this transformation is doing the whole functional transformation, but at the end of the day, what matters is a 0 is going to get mapped to a 0 where the location of the 0 in the Z domain is given by this expression Z naught equal to 1 plus S naught over 2 divided by 1 minus S naught over 2. Similarly, if the analog filter had a pole at S prime naught, then the discrete filter will have a pole at Z prime naught equal to 1 plus S prime naught over 2 over 1 minus S prime naught over 2. Okay. And basically that's how the discrete domain filters are designed. You say, I want a low pass filter. People already know the corresponding expressions of the low pass filters in the analog domain, which work well. And then they simply do a mapping of the poles as zeros to the discrete domain. And if the end filter ends up serving the purpose, it's a good filter. If not, you just go back. So there is a corresponding transformation also in the S domain. Of course, you can simply invert it. This means that S equal to 2 times 1 minus Z inverse over 1 plus Z inverse. So they are both, you can go from Z plane to S plane and from S plane to Z plane. It's an invertible transformation. I'm not going to go into the details of proving. It's a very simple proof that indeed if your S was imaginary axis, so what we said was the first criteria was if S is actually j omega, it's imaginary axis, then what that turns out is that your Z is such that absolute value of Z equal to 1. Okay. So if you are on the imaginary axis, your frequencies in the analog domain get mapped into frequencies in the discrete domain, which means your imaginary axis in the S plane gets mapped onto the unit circle. And the second part is that if S equal to sigma plus j omega is such that, so what makes S on the left half plane is if sigma is less than 0. Right? So if your real part of your S is less than 0, then you will live in the left half plane, and the requirement is that if you do this transformation, the end result ends up being that absolute value of Z is less than 1, which means that if you are in the left half plane, the resulting Z gets mapped inside the unit circle. And the advantages of doing this process is that we can get similar magnitude response, not frequency response, because the frequency response is magnitude response plus the phase response, and we know that IIR filters can't stable causal IR filters, we can't design them to have linear phases. So we can have similar magnitude response as an FIR filter, but with significantly less computational requirements. And the disadvantage, of course, as we talked about earlier, linear phase for stable causal IIR filters is impossible. So we'll leave the discussion of how to design IIR filters at this. In reality, what you can do is just you have these toolboxes available. MATLAB has a ton of functions available that you can use. The 4 common types that are used are, as I talked about earlier, Butterworth, Chebyshev 1 and 2, and elliptical. And I just want to briefly let you know what each filter is good for so that you can make a distinction. So Butterworth, it has the flattest roll-off. It has the flattest pass band, but the longest roll-off. What this means is that if you look at the pass band and the stop band, Butterworth filter actually, unlike the FIR filter using window method, Butterworth filter does not have ripples. Okay? It tries to be as flat as possible, but the trade-off is that it takes Butterworth filter a long time compared to other IIR filters to go to 0, or conversely from 0 to 1. Okay? So depending upon what you prefer in your application, if your preference is you don't want any ripples, then you want to pick Butterworth filter. The way you basically take care of the roll-off is you have to use more computational resources. The order of your filter has to increase. The number of poles and zeros that you need has to increase. Okay? Chebyshev, it does have ripples, but it doesn't have ripples in both the stop and the pass band. But either in pass band or in stop band. So based upon that, it's called Chebyshev 1 or Chebyshev type 1. So if it's in pass band, we call it type 1. If it's in stop band, we call it type 2. What do you gain by allowing ripple in either the pass or the stop band? Your roll-off becomes faster. So it has better roll-off than the Butterworth filter. And the last is elliptical filter or elliptic filter. And it has the best roll-off, but the compromise is that now you have ripples in both the pass and the stop band. So the message is that if you are really constrained in terms of your hardware and you don't care about linear phase and ripples, go with the elliptic filter. Otherwise, you can either go with Chebyshev or Butterworth. Okay, so I'm again going to go to this FDA tool. Just a reminder that behind this are function values that you can call yourself. But if I go to IIR, I say I want to design an IIR low-pass filter, it gives me the option of what kind of filters do I want. Okay, the bilinear transformation method that we discussed, basically we will care about Butterworth, Chebyshev type 1, type 2, and elliptic filters. So let's go by that. You give it the constraint that I want the roll-off to be within this range. So I say 0.2 to 0.25. I want it to go from pass band to stop band. MATLAB is going to design a minimum order, the smallest possible order filter for this, which will be a Butterworth. And when I do that, this is the response that I get. Okay. As you see that it may not look as, for example, good as the FIR filter picture that you saw earlier till you realize the scale on the y-axis. Okay, just this one block is minus 200 dBs. You are significantly attenuating this. This is like minus 1300 dBs. It's like all, for all practical purposes, it's zero. It's hitting zero very quickly. This is the order that you get, 41, which is sort of like, which corresponds to the summations and multiplications that you have to do, right? So if you go and look at, for example, the post-zero diagram, it has 41 zeros. They are all at z equal to minus 1, and it has 41 poles in this arc. Okay? So going back, what Butterworth means is there are no ripples either in the pass band or the stop band. Now it seems like the roll-off is really great, but I can ask the same design specification, not change anything, just say I want now a Chebyshev type 1 instead of Butterworth, and pay attention to the order of the filter here, okay, and the shape of the magnitude response. So I'm just going to click Design Filter, and because of the fact that I moved to Chebyshev type 1, I have now the order of the filter has gone down to 15. Okay. And type 1, as we talked about earlier, has ripples in the pass band, not in the stop band, but in the pass band. And if I zoom in, you see those ripples. Okay. They are really small because of the specification, but you see these ripples when we zoom in. I can go to Chebyshev type 2, which will replace the ripples in the pass band with the ripples in the stop band, depending upon what your application specifications are. In some cases, you want to make sure that the frequencies that you are letting pass don't get distorted at all, and at the stop band edge, a little bit of attenuation or less attenuation doesn't matter. So I'm going to do Chebyshev type 2, and this is what you get. And you get the familiar kind of ripples that you saw earlier in the stop band that you saw for FIR filter. Okay, but its pass band is now relatively flat. Here I'm zooming in, and you see that you don't see any ripple that you saw earlier in Chebyshev type 1. Okay. The order of the filter stayed the same, 15, from type 1 to type 2. I was able to maintain that. So whether you should use type 1 or type 2, there is no recipe for it. You have to really know the application that you are dealing with. Okay, now the same specification, let's go to the elliptic filter, and again let's pay attention to the order of the filter. And if I press the design, you see that the order from Chebyshev, it has gone down by roughly a factor of 2. You are now looking at an order 8 filter. So let's verify that. You have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 poles. So you have order 8 filter. Okay. And if I get to the magnitude response, you see that you have, of course, ripples in the stop band, but you also have ripples in the pass band. So that's the price you have to pay. Okay. Smallest order filter for the given specifications, but now you have ripples in pass and stop band. Now, how does even the worst filter does? So this is Butterworth filter, which had order 41 versus, let's say I want to go to FIR. And if I now design, the same specifications cost me 101. It's a 101 order filter. It has 101 zeros. You need a lot more computations than the Butterworth filter. But again, just reminding you, the compromise is, let's look at the phase. Right? You have a flat phase for FIR. I go to IIR, and I don't have a linear phase anymore. So this is group delay, right? Which is the derivative of your phase. So flat group delay means a linear phase, and this is not a flat group delay. So it's not a linear phase. So that's all that there is to know about general IIR filter design. A lot more details can be said, but as we talked about earlier, if you are really interested in applications where linear phase matters the most, you probably are not that interested in those details. So that then concludes our discussion of the IIR filter design to the extent that we wanted to discuss it. You should at least have a good sense of what are the general principles of Butterworth, Chebyshev, elliptic, which one is better in terms of order, which one is better in terms of flatness, and so forth. But we are not going to go into any more details. Okay, I'll just try to do a few problems from our earlier coursework because you may have been a little rusty in that, and since the final is cumulative, it's important for you to know that. So the first problem is basically saying this is your DSP block diagram, and the anti-aliasing filter is identity, so it doesn't matter. And the discrete time filter is identity, so it doesn't matter. So all that this system is actually doing is it's sampling your input and then reconverting a signal. So what is the only thing that can happen in this kind of a setup? So you get an input signal, you sample it, and then you reconstruct it. There are only two options. You either get back the original signal if you satisfied the Nyquist criterion, or if you did not satisfy the Nyquist criterion, then you get aliasing. And so that's all this question is testing. You are given one cosine and one sine. So this is a 3 kilohertz frequency, and this is a 4 kilohertz frequency. And you are given that the sampling duration is 2 into 10 to the minus 4. So your sampling frequency is 1 over 2 into 10 to the minus 4, right, which is 0.5 into 10 to the 4, or that is 5 kilohertz. So what do we know? Well, we should have sampled. We should be sampling at least twice the Nyquist rate. So the question is asking what is the output of the system. We know for a fact that YC of t cannot be equal to GC of t. Because we have aliasing. Why do we have aliasing? Because 5 kilohertz is neither twice of 4 kilohertz and 3 kilohertz. So now these are pure sinusoids, and figuring out what is your alias frequency is rather simple. We have the aliasing chart. You can either make the figure, or you can simply use the aliasing chart to go back to what frequency you will get at. At the very least, whether cosine or sine is a different thing, but you know that where the 3 kilohertz frequency will be mapped to in your input. Because if you have a 5 kilohertz sampling frequency, the maximum output frequency has to be is less than or equal to 2.5 kilohertz. So if you remember your aliasing chart, which we have done, which looks like this, you recover the same thing as your input, then you go down, then you go up, go down, and so forth, right? This is your Fs over 2, this is your Fs. So both of your frequencies lie in this region, and based upon that, you can figure out what your output frequency will be. Okay. The second question, you can ignore that because it's about Kaiser window, coming up with the values of beta and m. We just talked about Kaiser window design in MATLAB. We didn't really go over the formula, so we can ignore that. The third question is saying that we are given an endpoint sequence xn, and we are interested in computing the average. How can this average be calculated using the endpoint DFT? Okay. And what this question is trying to teach you is that the 0th element of your endpoint DFT basically gives you information about the average of the signal. So remember that the DFT formula is this: xn e to the minus j 2 pi k over n times n. What this question is asking is summation n equal to 0 to n minus 1 xn divided by 1 over n. So if I take k equal to 0, this means that x of 0 equals the summation of all the values, xn. So if I want to compute the average of the signal values, that is simply equal to x0 over n. Okay? So the 0th element of your DFT, which is effectively the 0th frequency. What is 0th frequency? That's just the DC component, right? So the 0th element of your DFT gives you information about the average of your signal. Okay, part D again is very simple. You are given a discrete time filter that is identically 0 at these frequencies. And it asks you to draw part of the pole 0 diagram. There may be other poles, maybe other zeros, but we know that the frequency response is identically 0 at certain frequencies. If the frequency response is identically 0 at certain frequencies, then we must have what? The 0, there should be a 0 on the unit circle at that value of omega. So we are given basically 6 locations where your frequency response is 0. So I draw this unit circle, and I must have a 0 at pi by 10 and minus pi by 10, right? So I have a 0 here and a 0 here at pi by 5 and minus pi by 5, and a pi by 2 and a minus pi by 2. Right? This is at least part of the pole 0 diagram. If the 0 was not on the unit circle, and you should of course draw what is this. So this location is e to the, for example, this is e to the j pi by 5. If it was not on the unit circle, your frequency response cannot hit 0 exactly. It can come close to 0, but it cannot hit. So if it's 0 exactly, it has to be on the unit circle corresponding to that frequency. Just like the problem we had in the second midterm. Okay, the next question, you can ignore that. We didn't formally do this kind of analysis. The next question is simply about relating the DFT samples to the continuous time frequency. So this is about the spectral analysis. The signal is sampled at 10 to the minus 4 seconds per sample. 1024 point DFT is computed, and this is the result that you get. Can we know anything about the spectral content of the signal? So what we are given is T equal to 10 to the minus 4, N is 1024 point DFT, and X of 200. So the first thing you need to do is convert K equal to 200 means little omega equal to 2 pi K over N. That's the discrete time frequency that it relates to, right? So every sample of the DFT, because this is less than N by 2, so there is a whole discussion that we had about which indices of DFT correspond to 0 to pi and which indices correspond to minus pi to 0. Since this is less than N by 2, this corresponds to simply this formula. And then this continuous time discrete time frequency corresponds to which continuous frequency? How do we obtain that? That is 2 pi K over NT radians per second. So we are looking at 2 pi times 100 over 1024 times 10 to the minus 4 radians per second frequency in continuous time. Okay. And then we have to do the scaling of the magnitude. So what's the relationship of the discrete of the DFT magnitude to or the discrete time magnitude to the continuous time magnitude? So this is the frequency that you are looking at in continuous world, and the magnitude is 1 gets transformed to 1 times t, which is 10 to the minus 4. Okay. So that's the relationship just looking at spectral analysis. Okay. The next question is, an audio signal of 3 minutes is input to a DSP system. If the sampling rate is t equal to 1 over 8 into 10 to the 3, the system has a total of these many quantization levels. How much storage in bytes is needed? Really simple problem. This was F. So G, basically we are told total time, so T total is 3 minutes. So that's 180 seconds. And your capital T is 1 over 8 into 10 to the 3 seconds. So you are collecting, this means that we have 8 into 10 to the 3 samples per second. So how many total samples did we collect? Total number of samples is simply multiply the total number of seconds times samples per second. So that's 8 into 10 to the 3 into 180. Now you're told that the system has 256 quantization levels. So remember the relationship between the number of bits and the number of quantization levels. Okay. So how many bits do you need for 256 quantization levels? that is equal to, so you just write it in the power of 2 form, so that's 2 to the 8 levels. This means 8 bits. So you have 256 different values. How many bits do you need? You need 8 bits to represent 256 different values, which is equal to 1 byte. So each sample takes 1 byte, and you have these many samples. So what's your answer? Your answer is 8 into 10 to the 3 into 180 bytes needed for storage. Okay. Quantization is something that unfortunately we did not cover in exam 1, and it wasn't a part of exam 2. It fell in the middle or at the edge of the two, so it's important that you basically be familiar with that. Okay, there is a similar kind of a quantization problem, I think, in the other practice exam. Okay, and part H is something that is briefly touched upon in the exam 2, which is what's the relationship between DFT and FFT, and the answer is FFT is just a faster approach to computing DFT. Right? We had some quiz question on that too in one of the Sakai quizzes. Okay, this next problem is again, if you understand the analog to digital and digital to analog parts, it's rather simple to see. You are given the classical DSP system, and what you are told is that this is the input, so this is the input GC of t, and you are given what you desire is this output. So YC of t is the desired output, which if you compare the two, you see that it is exactly the same thing, but with parts of the frequencies going to 0. Okay, so the immediate thing that should come to your mind is how do you accomplish this, that you kill part of the frequencies? What kind of a filter do you need? So what you need to do is have some sort of a band stop filter, which actually has this form that, sorry, I'm drawing the band pass. We need a band. So it needs to have this kind of a form where it keeps all the frequencies but kills these ones which correspond to the locations given below. Okay. So we need a band stop filter. You are given that HAA equal to delta T, so this anti-aliasing filter is effectively not there because it's an identity. And so it's a really simple problem. You need to make sure you pick the right T so that you don't have aliasing. And then you're asked to give the right discrete time filter. So if you know the shape of the filter in continuous time, you know how to do the conversion to discrete time. Right? So when you're doing filtering conversion, the only thing that happens is there is change of the frequency axis, no change of magnitude axis. So that's what this question essentially asks. The first part is express the range of values of t, so it should be such that no aliasing happens. The other is express the discrete time filter as a function of t. So that is simply taking that formation and coming up with the right discrete time filter. The third is sketching the Fourier transforms in discrete domain. So now these are Fourier transforms of these signals, and you know that Fourier transforms, when you go from analog to discrete, there is scaling of both the frequency axis and scaling of the amplitude. Right? So you will just do that simple solution for that part And then you are asked that the filter that you will get in part B, it will likely be an unimplementable filter. How will you change it to an implementable filter? Well, the answer I'm looking for is just a window method. So this is your ideal filter that we talked about. And when you do windowing, what do you see? You basically see ripples, and so the effective filter and filter that you will see will have this kind of a form. Right? So it's only asking you, do you understand what happens when you go from ideal to this windowing method? And then it's talking about adding another signal, WT, which is the noise, and you want to, in which case the input signal basically becomes sum of two Fourier transforms, so your input signal is not perfectly band limited, and so it's asking you to propose an anti-aliasing filter. So again, a simple concept, the anti-aliasing filter has to have, what is an anti-aliasing filter? An anti-aliasing filter is a Fourier transform AJA of j omega, which has height 1 and its cutoff frequency is minus pi by t to pi by t. Okay? And so really simple concepts from your analog to digital and digital to analog conversion.